History is being made in Geneva, Switzerland. Scientists from around the globe have been drawn by a single headline-making particle, the Higgs boson. So far, the Higgs boson has only existed in theory, holding together the architecture of how particle physicists view the universe. But it has never been observed in experiment. Now, 50 years after it was proposed, a paradigm-shifting machine is determined to find the Higgs boson. Is the Higgs merely a theoretical figment, or does it really exist? That's a question of science. Hidden within all nature's complexity is a fundamental question. What is everything made of? Today we know that all physical matter is made up of discrete units called atoms. Inside the atom is a heavy nucleus of protons and neutrons with lighter electrons orbiting it. Particle physicists have gone further into the atom. They've discovered countless new particles, both within the subatomic world and beyond. But what is the grand unifying idea that fits all these jigsaw pieces into one theory? Of all the emerging theories, one enjoys more popularity than others: the Standard Model of particle physics. This model has 12 building blocks of matter that make up the entire universe. Quarks are responsible for making particles like protons and neutrons. Leptons are another class of particles, which include electrons, muons, and neutrinos. These particles interact with each other through 4 forces: electromagnetic and gravitational forces, and the strong and weak nuclear forces. The remaining 4 building blocks are force carriers, each corresponding to a specific kind of force. For example, photons correspond to electromagnetic force, while gluons are responsible for the strong nuclear force. These force carriers mediate how the other 12 particles interact with each other to make up everything in the universe. But what makes the Standard Model so popular? Compared to others, it has the highest accuracy rate, with nearly every particle experimentally proven. But there's still one last empty space remaining, an elementary particle that continues to evade us.
You can always say the Standard Model explains everything, but you have the main cornerstone of that still not discovered. There is a linchpin in that, which was the so-called Higgs particle, Higgs boson.
So critical is the Higgs boson to the framework of the universe that it's been labeled the God particle in popular culture. But its postulation is not the work of a supernatural God. Rather, it's the handiwork of particle physicists around the world, including the Indian scientist Satyendranath Bose. In the 1920s, Bose's work drew the attention of none other than Albert Einstein. Their collaboration was integral to the development of quantum mechanics, and it inspired the postulation of a new type of subatomic particle. This was named boson in Bose's honor. Bosons, spelled with a lowercase b, are a class of fundamental particles. The Higgs is one such boson. But what exactly is it? One way to understand the Higgs boson is to rewind way back to the beginning of time. The instant after the Big Bang was unlike anything we know today. It was an instantaneous expansion. Temperatures were unimaginably high. Particles like quarks, electrons, and gluons hadn't joined to form atoms. Instead, they were whizzing about freely at the speed of light. So, how did matter form at all? According to the Higgs theory, as the universe began to cool down, radiation from the explosion began to thicken into a force field. Think of this force field as a thick sugar syrup. As particles encounter this syrup-like force field, they slow down, acquiring heaviness or mass. At this reduced speed, they can interact with each other to form atoms and other particles. This syrup-like field is the Higgs field, and it is mediated by the Higgs boson. Together, they give everything in the universe mass. And so, the Higgs theory explains the very basis of all existence. But when it was first put forward in 1964, its own existence wasn't easily accepted.
I wrote a short paper about that, and I sent it off to Physics Letters, whose editor was at CERN, and they rejected it.
I was told by Heisenberg that I was wrong, which was pretty scary for a young man who wanted to get a job. We knew that we had indeed done something that was very different and was very exciting, but we still didn't expect it to have anything to do with physical reality.
The audacious theory was the work of 6 people: Peter Higgs, Francois Englert, Robert Prout, Gerald Guralnick, C. Richard Hagen, and Tom Kibble. It was groundbreaking science hinging on the Higgs boson. But in the 5 decades since then, a glaring question has remained. Does the Higgs boson exist in reality? It has never been found in actual experiment. In the last century, tracking subatomic particles like the Higgs has been the work of particle detectors. These are devices that can identify or track particles by measuring their properties like energy, momentum, and electric charge, etc. Earliest detectors, called bubble and cloud chambers, could track particles as they moved through transparent liquid or vapor. But the more elusive the particle, the more sophisticated the detectors had to be. This is the Large Hadron Collider, or the LHC, stretching across the Swiss and French border. It's a path-breaking machine built by an international group under CERN, or the European Organization for Nuclear Research. So, how does the LHC plan to find the Higgs? By creating a mini Big Bang under 100 meters underground. This will be done by accelerating 2 beams of protons in opposite directions inside the circular ring. When the protons approach 99% the speed of light, they'll crash into each other. These collisions will occur at 4 points in the ring, where scientists can study them. The 4 corresponding experiments are called CMS, Atlas, Alice, and LHCb. Of these, the CMS and Atlas detectors are tasked with finding the Higgs. But what's the biggest challenge of locating the Higgs boson? The boson disintegrates almost instantly after its creation, lasting for only 10 to the power minus 22 seconds. So detectors can only identify it by measuring the resultant energies and particles it decays into. The CMS, or Compact Muon Solenoid experiment, is designed to do just that. It is built like an onion with a magnet layer and peels of particle detectors. Each detector layer takes a unique snapshot of a specific particle and energy. By analyzing them, one might find traces of the Higgs boson. But the LHC produces nearly 40 million proton collisions a second. In this massive haystack, how will a needle called Higgs be found? That's quite literally a job for the whole world. The global CMS collaboration consists of 4,300 people from 179 institutes and 41 countries. India joins it with 8 research organizations and science institutes. They will participate in building, testing, and installing the CMS detectors, creating software to process the generated data, and finally in doing physics analysis, including hunting for the elusive Higgs.
At present, we are about 30-32 physicists, and from there are about 10-20 scientific officers or engineers from various research institutes, and there are about 35-40 students.
India has built 2 CMS detectors. The Outer Hadron Calorimeter is designed to measure missing energies, which aren't accounted for by the newly formed particles.
The detectors, they are built so that they can run for 5 to 10 years. And the proton collisions produce lot of radiation. So the detectors have to be really radiation hard. They should not degrade in their performance. At the same time, the response from the detectors have to be very fast, say 25 nanosecond. So all these meant it's really a tough job.
The other major Indian contribution is to the pre-shower silicon detectors, which are crucial in identifying the Higgs particle.
This silicon strip detectors, they had never been built in India before, but we did it, and we made such a good quality of it at Bharat Electronics, BEL, in Bangalore, that when this experiment CMS ran short of some of those detectors, they approached us to make for somebody else's share, because they in fact couldn't make it.
But the Indian expertise in building particle detectors isn't new. It goes way back to long before the LHC came into being. In the 1990s, teams at Kolkata's VECC, a Variable Energy Cyclotron Center, built a detector called the Photon Multiplicity Detector, or PMD. It could track the exact number of photons created after a particle collision. Nearly a decade later, when the LHC was commissioned, the PMD was a perfect fit for one of its experiments called ALICE. ALICE, or a Large Ion Collision Experiment, is similar to the CMS. It recreates the Big Bang and studies the aftermath using a huge magnet and layers of detectors. But that's where the similarity ends.
ALICE is very different from the other LHC experiments because it focuses not on collisions of protons, but on collisions of nuclei. And this is, of course, much more complicated.
But why collide large nuclei rather than just protons? That's because by breaking a nucleus into quarks and gluons, scientists can study how it's built back again. To understand this mechanism, atomic nuclei are ripped apart inside ALICE. For a fraction of a second, the liberated quarks and gluons form a plasma, which scientists closely study.
By going to study the structure of matter in the infinitely small, you are actually also going backwards in time towards the origins of the universe.
When it comes to studying the quark-gluon plasma, India and ALICE are natural partners. In the past few decades, Indian scientists have been leading thinkers in this area. Now, the next generation is a big part of the India-ALICE collaboration, with 12 institutes from across the country. One of these is VECC, where the PMD, or Photon Multiplicity Detector, was first built. Now, engineers had to tweak it to fit into the LHC's design.
What happened for the LHC is that now we were in a confined space, so we had to search for a technology, for an option which would live for the next 10-15 years and also be fitted in this compact space.
So how exactly does the PMD track the number of photons?
This is my cathode. Again, this is my part of the cathode is this one. So I put this one, I put on top of that one, this one. From that point, I have another plate like this one. We flip it and then we put the soldering. So that forms my anode. So this whole thing is filled up with argon CO2 gas. That gas, when the charged particle goes through, that ionizes, and from the ionization I measure electrons on the anode. The signal which we get from each of the anodes, that the tracks which are there, that comes to the Manas chip. The Manas chip digitizes the signal, processes the signal, and that goes to the computer.
The Manas chip is one of the most significant technological contributions made by India to the LHC. It was designed by Kolkata's Saha Institute of Nuclear Physics and built by Chandigarh's Semiconductor Laboratory.
This has been really a flagship deliverable at CERN from India, because this has been tilded a product which went from our industry, a high technology and product, which is built completely in India.
The Saha Institute has also led the development of a critical part of the muon spectrometer arm of the ALICE, where back-breaking work went into developing some of the largest detector panels in the world.
Now this magnitude of the work as an assembled detector cannot be visualized also. This took 2 years of extreme effort by our technical team to build this detector. So not only this work was long, but also the quality control was very, very critical.
The successful business of setting up CMS and ALICE was a combined effort of scientists and technicians from around the world. For many Indian students, this was a once-in-a-lifetime opportunity.
The early days were really very good for us because all the members of my group, they were very new and they were first-timers in the CERN. And it was a kind of thing that, okay, we are going to CERN, we have to perform.
We are also a bit nervous, I would say, in a sense that what will be our role in this big experiment.
As it turned out, students were integral to the LHC's experiments. One such team has built the ALICE's high-level trigger system, a real-time filter that keeps the useful data from a collision and flushes out the rest.
We have developed an algorithm which can do this analysis as fast as within 1 millisecond.
Thanks to systems like these throughout the LHC, finding needles in the haystack of particle physics becomes easier, especially needles like the Higgs boson. Experiments at the LHC churn out nearly 15 to 20 petabytes of filtered out raw data each year. And so experiments like CMS and ALICE invite researchers from around the world to do physics analysis.
Our credibility as a country has gone up by the manifolds, which was not the case before. And India can be very proud today to have come a long way from the old days of obscurity and isolation in this to a center stage of the theatre.
And at center stage, every spin around the LHC is unfolding the cosmic drama of our universe. It's retracing our steps back in time, recreating the instant between nothingness and existence. It's a breathtaking moment in our collective knowledge. If the Higgs particle is indeed what made everything material, it must show up now.
We have a discovery. We should state it. We have a discovery. We have observed a new particle consistent with a Higgs boson. As a layman, I would now say, I think we have it. You agree? Yeah.
It's really amazing for me to find out that it's really enough, shall we say, enough for a discovery claim.
It shows, certainly to us, the value of just imagining.
This is extremely important because it really is the stone that shows that everything is in place.
This boson is a very profound thing that we found. Okay, this is not like other ordinary particles. It really is we're reaching into the fabric of the universe at a level we've never done before.
The outcome of this hunt has pointed physics in an exciting new direction, one that will keep scientists busy for a long time to come. As of March 2013, the LHC has halted. Instead, there are massive upgrades to take it into the next level of high-energy experiments. And so, we wait eagerly for the next chapter of the LHC story to begin.
The whole LHC experiments work so nicely. It's like a concert. Everybody does their own job very well. Then only a nice music comes up. So it's a music.
If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24 Qutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in.